What's the word?
All right, net ionics. All physical and chemical processes can be represented symbolically by balanced equations. Chemical equations represent those chemical changes. These changes then show how the atoms are rearranged in new combinations. They show that by balancing them, that we end up starting and ending with the same amounts. We have to have balanced equations. This is the conservation of mass law. It cannot be violated. It's not like, the speed limit where you're like, oh, I'll just go a little bit faster. No, in science, it is an absolute, okay? Balanced equation is a shorthand way to describe the changes that occur. They follow the law of the conservation of mass and matter that states that in any chemical or physical reaction, we can't create or destroy matter. Now, what is one way that we can destroy matter or change it? Change it from matter into something else, into energy. Not heat. It's not a chemical or a physical change. What is it? Nuclear. Okay. You can take a small amount of matter within the atom and change it into energy. Okay. That's the E equals mc squared, right? Where you take the mass that you are transforming times the speed of light squared, and it'll tell you how much energy you're getting out. Okay. So in nuclear reactions, we can have that happen. But in our world, in our normal everyday life, it can't happen. Okay. The number of each type of atom is the same on both sides of the arrows. We use coefficients, and that describes the number of particles. When we do these, the subscripts never change. Okay. Just your coefficients. We include states of matter. This is solid. Sometimes if it is in the form of a precipitate, it might use this interchangeably. So sometimes you'll see PPT written there instead of solid. Liquid, gas. And then AQ means that it is dissolved in water. When writing your chemical equations, remember your Brinkelhoffs. Some of you forgot that very quickly last chapter. Here are the steps for balancing an equation. Okay, write the equation. Count the atoms on each side. Compare the counts. If they're the same, you stop. If not, use the coefficients to make one element correct, recount, and then compare those counts. Remember, leave the singletons to last when you're balancing. Even and odd, we double the odd. Okay? Even and odd, double the odd. So if you're balancing an equation,
what is the charge of ammonium?
Mine +1.
Don't you dare. Don't you.
Okay, so here I have an even amount of oxygen. Over here I have an odd amount of oxygen. So even and odd, we double the odd. Remember that? Okay. Then you go back and compare. Well, now I've got 2 hydrogens times 2 is 4. I need 4 over here. So leave these singletons to last. Balance your compounds first and leave the single elements to last. Even and odd, double the odd. The oxygen was odd, right? 1 versus 2. Okay. Balanced molecular and complete ionic equations. Net ionic equations are different ways to represent these chemical reactions. The form used to represent the reaction depends on the context in which it's to be used. Once you've mastered the balancing the equations, which all of you, except maybe one, should be masters of these, writing the balanced ionic equation then comes after that. Remember, SNAP, S-N-A-P. These are always soluble, okay? Sodium, nitrate, ammonium, and potassium.
Okay.
You could also, if you don't want to remember SNAP, you could remember SNAC if that helps, since this is K on the periodic table. Okay? So either snack or SNAP.
I like snack.
Okay?
But it could be phosphorus.
These are always soluble. These are the ones that you have to know for the AP exam. They are the only ones that you have to know. All right, these are some sometimes, but you don't have to have these things memorized, okay? It's just typical things. Typically, these things are insoluble. Typically, these things are soluble. All right, precipitation reaction. This is our balanced overall reaction. We know that this is soluble because of nitrate. We know that this is soluble because of sodium. So these are going to be aqueous. We don't have to think about that. We see these things. This is automatically aqueous. Then you come over here. This has this guy and this guy in it. So this has to be aqueous. If they said something like, and your precipitate, you have 25 grams of the precipitate remaining, and they didn't identify the precipitate, you would know that this is the precipitate because this can't be. Okay? And this has to be aqueous, and there's two different reasons here why it has to be aqueous. Does that make sense? So then you would say, okay, this guy, and I made my circle a little too big there. This guy right here has to be the precipitate. Does that make sense? All right. So when we draw these out as an ionic equation, we write out the different ions. So this is a +2 ion of lead. We have 2 nitrate ions, and it's a -1. We have 1 sodium. We have, I'm sorry, 2 sodiums because of the coefficients, 2 chlorines, and then we come over here. Well, why did they not break this out? It's a precipitate, right? Okay. So then if we were to rewrite this as just the net ionic equation, this is the overall ionic. If we wanted to write this as the net ionic, we would get rid of the things that are the same on both sides. So this is the same, and this is the same as this stuff. So what remains becomes your net ionic equation. So this guy plus this guy yields this. That's your net ionic equation then.
Back to the last part. Why do we cross out?
Okay, so when we're writing our net ionic equation, anything that's the same on both sides that remains aqueous goes away. And I will explain to you why that is the case. Okay, so when we started out the reaction, we had 2 different containers here. Okay, 2 test tubes, let's say. In one test tube, we had this stuff. So we had some lead floating around, and we had a nitrate floating around in there. Okay, these are going to be floating around as ions. Why? In the water. Because it's soluble because of the nitrate. Okay, in this container, I have sodium floating around, and I have chlorine floating around. and it's soluble because of the sodium. All right. When we mix these together in the same container, I now have my lead nitrate down here. It's a solid. It's clumped down here in the bottom. I still have sodium and chlorine. Not chlorine. I did that wrong. Hold on. I screwed that up. I'm sorry, guys. Let's try that again. Yeah. Get rid of that too. All right. Let's start over. I have my lead chloride down here. That is a solid. It's formed a precipitate. It's precipitated out down to here. And I've got my sodium and my nitrate floating around. These haven't changed their condition. There's still free-floating ions in that solution. So because of that, we get rid of them in our net ionic equation. We only want to see what is actually doing something. The only thing that did something was the lead and the chlorine combined to form this. If these all remain soluble, then there's no reaction because nothing's changed. So if I had, for example, NaNO3 plus KCl, the K would supposedly go with the NO3 and the Na would go with the Cl. What do I have? They're both still aqueous, so there's no reaction here. Nothing happened. Nothing changed. These are still both aqueous. Everything's floating around still. All right. So that takes care of precipitation reactions. We spent a lot of time in regular chem on those, if you remember correctly. Days and days and days. All right. Equation here, and then
It's okay. You'll get there. Thanks, bud.
this is just showing that these are getting dissolved in water.
Woo. Okay.
Okay.
Hey, I do.
Are we already at it? I do?
Mm-hmm.
Oh, wow. Well, do you want me to just have you do the worksheet as a thing and then move the lab back to Monday and the quiz to Tuesday? Would that be better? So you don't have a quiz on Monday? And just not give you a work day tomorrow in class?
I don't really care.
Yeah, let's move it to
Okay. Well, we'll look at that in just a second. Let's finish
Actually, the quiz would be better Tuesday.
Yeah.
Okay.
And I want to, if we have questions, we can ask them on Monday.
Okay. That sounds good. We'll work as a class in a second to kind of rearrange that. Okay. So this is the rearranged equation that I was just talking about, kind of in a better format. All right. So here
Oh.
we've got ammonium carbonate. It's reacting with silver nitrate. It's forming silver carbonate as a precipitate, as shown in the image. I don't see an image on the right.
It's not on yours. It's on ours. It's like the yellow dye thing.
Really? Okay.
Oh, okay. Yeah.
Yeah.
So that's precipitating out. They want to identify the spectator ions in the net ionic equation. Okay, so we're going to write the balanced equation here. So NH4 2CO3 plus AgNO3 yields NH4NO3. See what we're doing here, Matthew, is we're taking, these are called anions here. They're negatively charged things, and we're swapping partners. These are positive charges. and we're going to swap the partners. So the NO3 is going to go with this guy.
So the
Why do they
2
switch?
should stay with the NH form. Does the
No.
subscript stay
No.
with the-
No.
And you know those guys are negative and positive just because you just remember it.
Well, this is a an ionic equation or ionic thing. This is a metal. So remember, anytime you have a metal and a non-metal, it's going to be ionic. So then you have to look at the charges. Silver is always a +1. Nitrate is always a -1. So these are going to be in a 1-to-1 ratio. So when we bring them over here, this is also a +1. This is a -1. So I don't need subscripts.
Okay.
Now I'm going to swap the partners here. So here the silver is now going to go with the carbonate. Okay. And I know that the carbonate is a -2 because I needed 2 +1s for every one of these. So this is a -2. This guy is a +1. So I'm going to need 2 silver to get this formula to balance out. Once I get my formulas balanced out, then I'm going to go and balance my entire equation. So now I look and I see, oh, I've got 2 of these on this side. So I need to put a 2 here. I can't put a 2 down here. I can't play with these subscripts once I got stuff in place. But then that gives me 2 nitrates. So I got to go back over here and get 2 nitrates. And then that takes care of my silver. And then I need to put down the fact that this ends up being a solid. And this is going to be aqueous. Okay. So identify my spectator ions. So what things are going to remain aqueous on this side? It's these 2 things. So 2 NH4 +1 and 2 NO3 -1. They're called spectators because they're not actually changing. Nothing changes about their condition. Over here, they were aqueous. Over here, these things were aqueous. This remains aqueous, and this remains aqueous. So both of these things remain aqueous. If they remain aqueous, they're spectators. Now, what's participating in the game? Then we look and we see, okay, what is taking place here in the game? Well, my silver is becoming a solid, and my CO3 is becoming part of that solid. So that's what I'm going to write down here as my overall equation. So I'm going to have CO3 -2 plus AG, and I got 2 of those, +1, and I'm going to, and that's AQ. And then that's coming together to form my solid. This is all that's changing. So that's your net ionic equation.
I smelled it.
Good? All right. See if you can write this guy out. Ben, go over and work with Matthew and show him what you're doing.
Okay.
Be nice.
Which one? We're doing what we do. Yeah. I did all the you do.
How do we memorize what the chart is?
Yeah.
You don't need to.
What's the charge of copper?
Right here.
Oh.
Hydroxide is -1.
Yep. And you can get that from here. Okay. So if you know that potassium's always what? It's always a +1 because it's in the first column. So if you know that this is a +1 and these are in a 1-to-1 ratio, what does hydroxide have to be? It has to be a -1. Oh shoot, that's still gonna put a quiz on a Monday.
What?
No, I'll fix it. Just hold on. Control X.
You're
I
switching
just- I'll switch these 2 days around.
with NO3, and copper goes with OH. Alright, and you just need to do, because OH is a -1 charge, and copper is a 2 because it says that we're using copper 2. So you have to do, and OH is a polyatomic ion. So you do parentheses. So then when we write our overall ionic, we have to separate everything. So Cu 2 plus parentheses 8 plus NO3 so -1 parentheses 3. Oh wait, we gotta balance this first. No we don't. No we do.
I don't think Ben's gonna be very helpful.
I am. Okay, so when we balance it, we have to balance it. So there's, how many OHs are there on one side? There's yeah, so that means we need 2 on the other side. So we gotta put a 2 in front of there. And then, because now we have 2 potassium, we need 2 potassium on the other side again, so you gotta put 2 in front of that. And then there's 2 nitrate, so that means, but there's also 2 nitrate on the other side, so we're all balanced.
Yeah, overall we just split
Okay,
compounds.
Okay, so let's
Weird.
you just separate all the stuff, so you basically have
Yeah.
positive ion and
Potassium.
negative.
2
Okay.
hydroxide. Stupid.
And then you have 2K,
There's like no space.
which is
Do you have to put all the charges?
Mm-hmm. Otherwise, they're not ions.
how do you know?
It's a net ionic equation, so you have to put the charges on there.
Oh, okay, so copper has a 2 plus 2 charge, and nitrate only has a 1 charge. So you would do the small subscript there, because when you do the big one, that's affecting both. Yes, it only affects the one there. Yeah, and the parentheses is needed, because if you didn't, you would just put like NO32, it would be used for the oxygen. So if you have like NaCl, you don't need anything, but if you have like BRC, MgCl, Mg has a +2 charge, and Cl has a minus, so you get 2 there, you don't need parentheses because it's only.
Oh, I screwed this up.
So then you have that, and then you got your arrow, and that forms to create CuOH 2. But we keep that together on the other side because it's a solid. It's not aqueous. Because that's because it's hydroxide, so it's like nitrate. It's not like 1 It's mixed together as one
These
solid
solid, so
ion.
I'm gonna separate like how this is a
So it's like nitrate.
since it's in
So just think of OH as
in most cases, we'll just write the
whenever you use it, you keep it
Wait, so in
together.
the overall ionic equation, we don't need
Because
to
this is
include like the state of matter?
Unless you're forming
essentially like
Because it's aqueous or.
this word.
You should. I just got lazy.
use the OH
Try and write out
another name,
temperature, temperature separately than
water.
So like for this one,
So we have the CuOH2 solid, which we keep together because it's a precipitate, it's not aqueous. So we only get this last thing.
Nitrate.
Then we have 2 potassium again, which is
oh, like a
plus
solid.
aqueous,
So in this
Plus
question, it says
2 NO.
copper hydroxide is precipitate, and if it's precipitated, then it's solid. Whereas this is